Hi everyone, welcome to the second video for Module 1 of Knies 7103, Design and Analysis 1. So in the first video we were talking about the broader theoretical framework for this course, where we're going to be considering data as a function of our model and the error that's left over, right? And the error being the difference between our model and the data. In this video, we want to get you a little more comfortable with some of the formal notation that we'll be using in the course, and just make sure that some of the terms that we're talking about and the levels of analysis that we're talking about feel a little more comfortable if it's been a while since you've had a statistics course, or if some of this material might be brand new. So a big part of design and analysis is being able to translate our narrative hypotheses, for instance, that there is a beneficial effect of exercise on resting blood pressure, into statistical hypotheses, right? And actually being able to say formally, what is the statistical test that corresponds to that hypothesis? And how do I write that down as a formula? And then how do I test it in practice? So in order to do that, we need to learn a bit about formal notation, elaborating on our general framework of that data equals model plus error. And we can rewrite this to be a bit more formulaic with y sub I is equal to what we'll call y hat sub I plus epsilon sub I. Now, y hat, right, with that little circumflex accent there, is the estimated value for the ith observation of our data, right? So for instance, if we had 10 people's heights, y sub I, right, we'd have y1 would be the height of the first person, y2 would be the height of the second person, y3 would be the height of the third person, and so on. So we can index, hence the I, which observation it is using that subscript. And then we can differentiate the actual data, right, the actual y, from the estimate, which is the y hat. And the difference between those two, right, if we just moved this to the other side of the equals sign, the difference between those two would be the error, or epsilon. So we could also expand the y hat term because the y hat is our model's prediction. So we can actually write that out more long form as our whole model. So for instance, if we had a conditional model in which our estimated value of y depended on one other variable, we could write it as y hat sub I is equal to beta 0, right, some intercept, plus beta 1 times x sub I. So for each individual, they have a y and an x. And we're going to generate a y hat, right, a predicted value based on their x. So in this case, we have a conditional model in which y is conditional on x, and it's a simple linear model. But we could rewrite this more completely then, and I've color-coded this to show that our data is equal to our model plus some degree of error. And for each individual data point, right, each sub I, we have some x's, some independent variables in our model that are leading to that prediction. But we're also going to have some unique errors. We're going to have the difference between what our model predicts for that person and what their actual score was. And that's the residual error, or the error that is left over after we've done that subtraction. So it's also important to distinguish between what we would call parameters, which we represent using the Greek letters, beta, sigma, epsilon, etc., and our estimates of those parameters, which will be represented using Roman letters, so for instance, B, S, and E. We refer to a parameter in our model as sort of any variable we insert into it. Right? Now, the true value of that parameter is not knowable, right? It is some value in the population, and in theory, if we could measure everyone, we could determine what that parameter is. But we can't do that, right? So we need to estimate those parameters from our sample. So oftentimes, we will write the formula for our model with the betas as parameters to say, okay, this is what we're saying our model is. But the actual values that those take, like let's say that I think height relates to weight, maybe if that beta is, maybe it's like 60%, right? It's 0.6. Or there's a positive relationship, but it's not quite 1. It's not a 1-to-1 correspondence between height and weight, right? That what we would call a fitted value, once we actually assign a number to this beta, it's actually a B, because that number comes from the data in our sample. So that fitted value is an estimate. It is an estimate of the population parameter. So again, if we had access to the entire population, those true values of the parameters would be knowable, but that's almost never the case. And usually we're interested in applying the results of our study to a large group of people, right? So we're going to try to measure maybe older adults or postmenopausal women, or adults with a history of heart disease, right? Whatever our population is, we're going to sample from that population, and we'll probably try to get a big sample, and we're going to try to get a representative sample, but it won't be everyone. So then we have to make an inference about the fitted values, the estimates that we see in our data, and the parameters that exist in the population. And when we're trying to estimate these parameters, it's also important to think about how the sample size has an influence on the variation in what we would see. For instance, if we're trying to estimate an intercept, let's call it beta 0, smaller samples are going to lead to larger sampling variability. So in this case, let's say I took 10 people, another researcher took a sample of 10 people, and then another researcher took a sample of 10 people. Those could all be very different estimates, because 10 is not a lot of people. Our samples are probably going to be really bad estimates of the population parameter. And they're probably all going to disagree with each other. Some might be higher than the true value, some might be lower. Some might be positive, right? And some might even be negative, depending on what it is that we're measuring. But when we have relatively small samples, we're going to expect a lot of sampling variability and a lot of disagreement between experiments. When we have larger samples, so let's say we take 1,000, this should be a lot smaller. So again, if I run an experiment, someone else runs an experiment, a third person runs the same experiment. We're all sampling from the same population, so we're all trying to estimate the same value, the parameter beta 0. But we're going to get individual fitted values, right? Individual estimates of that parameter that are slightly different. But with really large samples, they're going to agree reasonably well. And a good sort of thought experiment for this is, let's say that we have everyone in the room, okay? If I wanted to estimate the height of everyone in the room, and I wanted to sample from the room, well, the largest sample I can take and still have it technically be a sample is to get everyone except one person. So I'm leaving one person out. And then if I sampled again, so now I randomly select everyone, but I leave one person out. Leaving that one person out each time isn't really going to change the average height in the room too much, right? Depending on how big the room is. But now let's say I only took 3 people at a time. If I randomly select 3 people and I average their heights together, I might randomly sometimes choose 3 very tall people, or randomly sometimes choose 3 very short people. And in my smaller samples, outliers are going to have a much larger effect. So it's important to remember that these parameter estimates come from the data that we observe. And although they are informative, if we had taken a different sample, the data could look very different. So we need to think about how much sampling variability we're going to have due to chance fluctuations. Sort of, if we assume that random sampling is the only factor operating on our data, how would these data look different if I went and took a different sample of 10 people? And if I'm only taking 10, it could look very different. If I'm taking a sample of 10,000, it's probably a lot more stable from one sample to the next. So all else being equal, the variability between samples is going to depend on sample size, which is often denoted by n. And this usually is going to be a lowercase n if we're talking about a group of people. Sometimes it might be written as an uppercase n if we're talking about all people in an experiment. But n is usually a letter reserved specifically for referring to groups of people, either everyone in the experiment with a capital N or subsections of the experiment with a lowercase n. And as we will discuss, we want to use the data from our sample to make inferences then about likely values for the parameters in our population. Like we said, we're going to get some estimate. We're going to get some fitted value when we take our sample. It might not be a great estimate, so we need to put some error bars around it and say, okay, well, we observed that the average height was maybe 165 centimeters. Right? But it could have been anywhere between 135 centimeters and 195 centimeters. So we have an estimate, but it's very imprecise. Okay, and we're going to learn the mathematical formalisms for drawing those confidence intervals around our sample estimates, and we're going to learn how to accurately make an inference about what we observe in our sample and relating that back to what might be happening in the underlying populations. And critically, we're going to learn about the assumptions that we're making in order to make that inference. Okay. So in order to do this, right, as a starting point, we're usually going to have to calculate some measure of central tendency and some measure of spread. Hopefully those terms sound a little bit familiar to you, but no worries if they don't, right? But a measure of central tendency, exactly as it says on the tin, is some measurement that tells us about how data are clustering together. So the mean, the median are both measures of central tendency. Measures of spread tell us about how different sets of numbers spread out. Are they densely clumped together, or are they relatively fanned out and distant from their central point? Okay, so the mean is a very common one that we're going to use, and in the subsequent lectures we'll talk about why. But the mean we'll often denote using this bar as an accent mark. Okay, so y bar, if you see it written like this, is the mean of all the y's. We could also have an x bar or a k bar, depending on which variable name we're using. But if these are my y's, right, these numbers here, y bar is equal to the sum of y sub I divided by n. Okay, so that would be each y, right, because y sub I, y1 is 15, y2 is 25, y3 is 22, and so on. So I have to sum all of those values and then divide by the number that there are, which is 6, right? 1, 2, 3, 4, 5, 6. So I'm dividing by 6. We can also calculate the variance, which is a measure of spread, which is how different these numbers are from each other. And the variance, in case you are not familiar with this calculation or this formula needs a little bit of refreshing, the variance is the sum of each y minus the mean squared divided by n minus 1. And in subsequent lectures, we'll demonstrate why we need to use n minus 1 rather than n when we're calculating the variance. But for now, just take it as given that it's n minus 1. But we're going to take, again, each y minus the mean. So we'd have to calculate the mean of these 6 numbers, and then we would calculate a difference. So we would take y1 minus the mean. So we do 15 minus the mean, 25 minus the mean, 22 minus the mean, and I'd end up with 6 deviates, and those deviates are the difference between each score and the mean. I would then square each of the deviates, right, and then add all of those squared deviations together. So I'm going to get the sum of squared errors here in the numerator of my variance formula. And then I will divide the sum of squared errors by the number of observations that there are minus 1. So that gives us the mean squared error, or the variance in more standard terminology. And that tells us how far away scores are from the mean on average. Now, the difference here is that it's in squared units. So that's not always the most informative, so sometimes we'll take the square root of the variance to get a number that we would call the standard deviation, and the standard deviation is simply the square root of s squared. But they're measuring the same thing. The only difference is that the variance is in squared units, the standard deviation is in the original units because we've taken the square root of the variance in order to calculate it. All right, so that's it for this module, and I'll see you in the next video.